members of the Institute for their kind invitation. So my name is Takei. I'm from CUNY Queens College. And this work, I'm going to be talking about spin current and noise across biased quantum spin chains. This work was done by my PhD student who just recently joined. Most of the technical calculations were done by Josh Aftergood. Okay, so I'd like to start off just motivating why we like to study this problem, and then look at spin transport across to the spin-and-a-half antiferromagnetic chains. Look at two ways of biasing the quantum spin chains, looking at population bias as well as thermal bias. I'll explain this in a second. Look at spin current and noise, and then define spin Fano factor, which might be experimentally measurable with sort of current spintronics experimental technology. And then I want to compare this result to spin transport across two biased Magnon bats and see what are the similarities and differences between these two types of transports. And then I'll summarize and give an outlook at the end. Okay, so the motivation for this work is rooted in a series of experiments done in spintronics area where they look at non-local current drag that's mediated by diffusing magnons in a magnetic insulator. So the type of system, the setup that I'm talking about here is you have a magnetic insulator. YIG is typically used in spintronics. And then you have a platinum contact on one side, which has a current driven through it by spin Hall effect that generates a spin current, which creates a non-equilibrium accumulation of magnons here, which causes them to diffuse. And if the spin diffusion length is long enough compared to the separation distance between the two platinum, the magnon current can be collected at this platinum contact, and the spin current can be detected using electrical voltage by inverse spin Hall effect. And so, of course, this is interesting from application point of view because you can transport electrical information from one place to another via an insulator, which has no moving electron charges. So it could be applied for energy efficient classical information technology, transferring information. But from a more theoretical point of view, I think this opens up a new avenue of research that I'm particularly interested in, and it's to look at two-terminal spin transport through more general insulating system. And I think that goes well with the title of this whole conference or this workshop, which is collective spin transport through electrical insulators. Electrical insulators don't have to be magnetically ordered. It can be magnetically disordered, but still have mobile spin excitations, which can transport spin from one side to the other. So this, I think, is an interesting direction. One area in particular, we can study maybe two-terminal spin transport through more exotic magnets like quantum spin liquids and quantum spin ices. And there are some material candidates which are popping up. But I think it's still, this field is still controversial, so it would be nice to look at these types of systems from a new perspective of spin transport. So that's sort of the general motivation. But a more particular system that I want to concentrate in this talk is a spin-and-a-half antiferromagnetic chain. For example, the XXZ model. And this is a nice model in particular because it's amenable to rigorous theoretical analysis like bosonization and various numerical techniques. And it's also relevant to experiments. So a few years ago, there was a nice sort of comparison of the spin dynamics in this system probed via NMR. And it showed very nice agreement between experiment and theory. Also, more recently, a year ago or so, there was a report of spin-Seebeck effect in quantum spin chains. They attribute part of this inverse spin Hall voltage signal to a transport of spin excitations from the quantum spin chain into the platinum that's attached nearby under a thermal gradient, temperature gradient. And so this at least sort of demonstrates the possibility to measure spin current that's flowing out of a quantum spin chain using platinum contact, very much in line with the two-terminal non-local current drag type setup I was talking about in the beginning. So I think the experiments are sort of approaching that direction where they're looking at spin transport through more sort of exotic quantum magnets. So now I want to talk about what we should expect when we try to inject spin into a quantum magnet. So in general, local injection of spin 1 excitation into a quantum magnet should depend on the effective quantum spin number S of the localized spin. So imagine I'm trying to inject a spin 1 excitation into a quantum magnet. For a large S magnet, you can put in multiple spin-on excitations into a local site. So the theoretical description of injection is in terms of basically tunneling bosonic quasiparticles, or the magnons. And that's what I sort of call the Holstein-Primakov paradigm. But if you're trying to inject spin 1 excitation into a spin 1/2 quantum magnet, then you cannot inject 2 or more spin 1 excitations into a single site at a time. And so the theoretical description of injection process should be in terms of tunneling spinless fermions. And this is for spin 1 system, one-dimensional quantum spin chain. You have this Jordan-Wigner transformation, which basically maps the Hilbert space of a quantum spin chain to Hilbert space of interacting fermions. So here, the tunneling process should be in particular subject to Pauli blockade. Pauli exclusion principle, basically. So it should give very different signatures as you move from a bosonic paradigm to a fermionic paradigm. So what I want to address in this talk is what are the experimental consequences on spin transport if the spin transport is now subject to this Pauli exclusion principle, and what are the direct sort of measurements one can try to do to look at this difference in sort of a spintronics experimental setup that's emerging these days. Okay, so the system of interest, I have 2 spin 1/2 XXE antiferromagnetic chains, which are weakly coupled at a single contact point. So I have one spin chain, which is the injection chain. I have another one, which is a measurement chain. And there's a coupling here. I'm just going to assume for simplicity it has axial symmetry about z-axis. So the spin current that I'm talking about is the conserved component of the spin current, which is the z-polarized spin current. And I'm going to consider 2 types of biases, population bias and thermal bias. Population bias refers to, let's say I have a platinum contact here, which via spin Hall effect injects spin current into the injection chain. And the spin current will flow and sinks into the drain here. But some of that spin current may tunnel across through the coupling into the measurement chain. And the measurement chain, the current will split up into left-moving and right-moving currents, each of which can be sort of detected by a measurement contact, platinum contact by, let's say, inverse spin Hall current. I'm also going to consider temperature bias in which the upper chain, the injection chain, is at temperature T1, and then the lower chain is at temperature T2. So I'm going to consider simultaneous bias of this type and look at spin current that's tunneling across at this contact point and also the noise in that spin current. Okay, so theoretically, what we can calculate quite easily is this spin current that's tunneling across the 2 spin chains and its noise, and we can define a Fano factor to be the noise to signal ratio of that quantity. Experimentally, I think what the experimentalists can sort of access are these currents here generated in the platinum contacts. So the spin current impinges on this platinum contact, which through inverse spin Hall effect will generate a current. They can measure that current and the noise. And so that's sort of at the total current. So if one adds the current that's generated here and add them together, you get the total charge current. And the experimenters should have handle on this total charge current and also the noise in that. However, if you want to link these physically measurable quantities to the Fano factor that we calculate, then there's sort of an effective spin Hall angle that enters, because the spin current that's impinging on this platinum contact should generate an inverse spin Hall voltage, but there must be some conversion that goes on, which depends on all sorts of microscopic details of this interface and the mechanism for spin to charge conversion. So I'm going to lump all of that sort of into this parameter spin Hall angle and just assume that the charge current that's generated by this impinging spin current is just proportional to the spin current. But that spin Hall angle sort of enters in the expression for Fano factor that we can calculate. So without knowing this, we cannot directly link what the physical quantity that they measure and the Fano factor. However, I'll show at the end that if you do some control experiment, we can extract this data experimentally before we go into doing the actual experiment. Okay, so I'll talk about that at the end. Okay, so the model is that I have 2 quantum spin chains, XXE model, which is coupled via this usual spin-spin coupling at the contact point. And then the long wavelength theory for this XXE model, we can bosonize it, well, use the Jordan-Wigner and then bosonize the fermion model to Tomonaga-Luttinger theory. And then you get this sort of bosonized Hamiltonian. And then the magnetic field bias, or the bias that injects the spin current into the system in the bosonized language, can be written in this form. And the mu here is basically the population bias that's acting to inject the spin current into the quantum spin chain. Yeah, so I'm just assuming here antiferromagnet, quantum spin chain, and I'm allowing for JZ to be different from JPerp. So it's uniaxially symmetric about the Z-axis. No, I'm assuming it's smaller. I'm assuming it's smaller because if this goes to, this is larger than JPerp, then it will flow to a different fixed point. Yeah, yeah. So it's easy plane. Yeah, yeah. JZ is a bit weaker than JPerp. Yes. This one here, SU2 symmetric. Yeah, so there is an isotropy within the chain, but between the chains, I'm assuming it's SU2 symmetric. This would be, yeah, just for, actually, but if you include an isotropy in the coupling here, if you're calculating the JZ part, the current Z-polarized spin current, once you take the commutation relation to calculate the spin current operator, the JZ actually, the Z component doesn't really play a role, actually, anyway. So as long as you're looking at the Z-polarized component, shouldn't play a role. Yeah. Yeah. Yes, 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 there's two terminal, yeah, yeah. Yeah, so I'm just saying that, yeah, I mean, it is interesting to look at also just injection of spin current into a single chain. I'm assuming here that I'm kind of interested in the noise properties. So if you were to do a one spin chain problem, you need some sort of potential or something to create a reflection. So something that creates a noise. If you're just injecting it into a clean chain, basically you don't get any noise generated on the collecting platinum contact. Yeah. Yeah, one chain won't give you anything for the noise and Fano factor and so on. You could still have, you know, this problem is exactly the same as just having two spin chains which are coupled end to end weakly by some exchange coupling or something like that. But for simplicity, theoretically, it's easier to model two infinite chains and then just couple it at a single point. But I don't think the physics should change, even if you have two end-to-end coupled chains. Okay, so so the theory is that, okay, first we define the spin current operator to be spin current that's leaving the injection chain. And you can calculate this within the linear response to lowest order in the coupling constant, JC. And the Keldysh calculation, in principle, you have to calculate the expectation value as current using Keldysh formalism, but as long as you're looking at lowest order in J sub C, the linear response calculation is actually equivalent to a Keldysh calculation. So we define the thermal average in chain 1 with respect to the bias Hamiltonian and the spin chain Hamiltonian at temperature T1, and thermal average for chain 2 to be the spin chain Hamiltonian and at temperature T2. The lower chain doesn't have the bias term. So then you can calculate using linear response, and the results are here. So the spin current basically looks, the noise and spin current and the noise look almost exactly the same, except for this sign factor here, which is sine of mu. Mu is the population bias, and the noise comes with a cosine factor. But rest is pretty much the same, but this turns out to be very important. This is actually a direct consequence of polyblocking physics. Okay, so before I go into actually looking at more the results in more detail, let me compare this to a Magnon noise. Imagine that you have now two Magnon baths. One is at, let's say, chemical potential mu and temperature T1, and you can have a finite chemical potential for a pumped Magnon system, for example. And then that's coupled to another Magnon bath, which is a chemical potential 0 and another temperature T2. And then you have a platinum contact attached at the end of the second Magnon bath. And so the spin current that's tunneling across due to this bias may reach this platinum contact and then generate a inverse spin Hall current. And that's something that experimentalists should be able to measure. So imagine that I consider, for just concreteness, two largest Heisenberg ferromagnets in a uniform magnetic field, and so the Hamiltonian can be written in this form. And for large S, you could basically model it as a non-interacting boson gas with a dispersion relation there for the magnons. And we write the usual exchange coupling, interfacial exchange coupling between the two Magnon bats. And let's calculate current for this simple case. And so here here's the how to experimentally determine this Fano factor. Again, the noise in this current and this current is what the experimentalists can measure, but related to the theoretical spin Fano factor, there's always an effective spin Hall angle, again, entering, because I'm assuming that the spin current that's impinging on this platinum, or the spin current that's tunneling across here, will generate charge current, which is proportional to that, with all the details sort of hidden inside the spin Hall angle, and that will enter here. So we need to somehow do a calibration to actually get the spin Fano factor. But I'll talk about how you can do that experimentally. So the theoretical result for the current is here. G of omega is the Magnon tunneling density of states, and the Fano factor can be expressed with the usual ratio of noise to signal. So let's look at the results. For the spin Fano factors, let's look at the Magnon case first. I can define the shot limit, so to speak, when the population bias, chemical potential of the first Magnon bath is much larger than the base temperature, the temperature of the second Magnon bath, or the thermal bias is huge, where tau is a dimensionless thermal bias parameter. And then you can show that spin Fano factor actually approaches h bar. And that just says that you have a Poissonian tunneling of magnons, each of which carries angular momentum of h bar. So that's kind of expected. However, for quantum spin chain case, the large population bias, if you bias the injection chain by a large current, you can again reach this shot limit where a Fano factor approaches h bar. But for large thermal bias, F actually diverges to infinity. So basically this tells us that spin-Zabek effect cannot lead to a large injection of current through a quantum spin chain within this model. Okay, so let's understand what this means, and the fact that both of these large bias limits approach h bar and this one doesn't is a direct consequence of this Pauli blockade physics. So this diverging Fano factor in the quantum spin chain case is Pauli blockade, and basically you're trying to you have a coupling between two spin chains, but if you map the coupling Hamiltonian between the two spin chains to Jordan-Wigner fermions, it's just you can map it basically to tunneling of fermionic quasi-particles. So it's subject to spin blockade or Pauli blockade. And so if you try to inject too many of them, or many of them at the same place, you cannot do it. And especially when the bias of the two spin chains, the relative bias becomes equal, the phase space for you to scatter fermions, to have a net flow of fermions, actually go to 0. So this, if you notice the spin current expression for the quantum spin chain, the bias effect, the population bias effect, and the thermal effects all decouple completely from each other. So if you set mu to 0, no matter what the T1 and T2 are, the current is identically 0. So the phase space is basically squeezed up because of this fermion nature of the tunneling process, that there's no net spin current flow. But of course, a noise has no such pinching. The cosine of mu, 0, is still 1, so you do have finite noise. So basically, for 0 bias, population bias, S remains finite, but I goes to 0. So you basically have a divergence of the spin Fano factor. S over I diverges. And that's true for any thermal bias, T1, T2. Yeah. No, so it has two contributions. It's looking at Johnson-Nyquist and also a shot at the same time. Yeah. Yeah, so Right. So this is in the case of okay. So in the case of right. So spin current here. Okay. So when mu is going to 0. Right. So this is always there. Okay. Let's say you have no temperature bias or anything. So yeah, there will be some noise, just Johnson-Nyquist. Now, you can also go to 0 temperature. Let's say you go to completely 0 temperature limit. you could still get finite noise and current. And that's the limit that we're interested in. Basically, the temperature is very low compared to the population bias. Yeah. No current, but yeah. So here, even if you send the temperature to 0 in both of these spin chains, if the population bias is 0, if you send population bias to 0, you get 0 current, but you still get, here you get, let's see. Okay, that's a good question. I have to think about that. Maybe we can talk about it later. Yeah, it's a good question. Yeah. But here, the spin-Seebeck effect will not generate a tunneling current in the unbiased quantum spin chain system. So you need a non-zero population bias to open up phase space for net spin flow between the chains. Okay. This sort of suppression or this effect of polyblockade is also there for the noise itself. So this is now the case where I'm sweeping the chemical potential of the first chain through 0 and then to a negative value. I start off at a positive population bias and then I go through 0 and then to a negative bias. And then the noise itself also has a dip at 0 chemical potential. And this is also, we attribute this dip also to polyblockade physics because now charge fluctuations or the spin excitations can tunnel across, but due to polyblockade, those fluctuations are sort of suppressed when there's no net chemical potential bias between the two chains. So that can also be sort of detected. And then at the end, I will try to talk about, just to finish, talk about experimental extraction of the spin Hall angle. So if you go to the shot limit, then with the population bias, then for both the spin chain case and the Magnon case, you can go into the regime where Fano factor approaches h bar. So imagine that first you bias your two systems, the spin chain or the Magnon scenarios, to a large bias limit. In this case, Fano factor should reach h bar, and so the spin Hall angle can be extracted by this ratio of the noise to current. And so first one can do this kind of control experiment to extract the spin Hall angle, and then once you have it, then you can go into other regimes to detect, relate the theoretical spin Fano factor to the experimentally measured ratio of the Fano factor. Okay, so I think that's all I wanted to say. So to summarize, I hope I convinced you that looking at the spin Fano factor can be interesting and that it reveals underlying quantum statistics of the tunneling spin excitations. And there's a nice sort of crossover between bosonic tunneling physics to fermion tunneling physics as spin quantum number approaches the quantum limit. And spin Fano factor can also provide a new way to kind of experimentally detect effective spin Hall angle by not just looking at the current, but also looking at the noise. Maybe gives a way to experimentally detect this spin Hall angle for in similar ways. This was done for in the spintronics experiments. People use broadening of the FMR line width or torques, measurement of torque to get the effective spin Hall angle. But hopefully this will give a new way to do it. And possible new direction is to look at effects of Magnon interactions. So far the Magnons are non-interacting, but if you include interactions, then it's known that it gives renormalization to spin Fano factor. So it's interesting to also look at interaction effects. And also, because if this all relies on a single site coupling, then in real experiments, maybe multiple sites are coupled. So the effect of multiple site coupling, that might alleviate some of the polyblocking physics if you have multiple sites to tunnel into. So that's something that we can also look at as well. Okay, so with that, I'd like to end. Thank you.
Questions?